All right, so I'd like to do example 16.2 from the textbook. So the problem there is to maximize 2x1 plus 5x2 subject to a few inequality constraints. So first of all, we're saying x1 can be at most 4, x2 is at most 6, x1 plus x2 is at most 8, and x1 and x2 both have to be non-negative. All right, so this is our problem. And we'd like to use the simplex method to find the optimal pair x1, x2. So the first thing to keep in mind is that if you want to use the simplex method, your linear program has to be in standard form. There are versions of the simplex method that work when your linear program is not in standard form, but for us, it's just easier to put it in standard form first. So remember that standard form means we're minimizing instead of maximizing. All of our variables are non-negative, and our only constraints are equality constraints. So that's the big one. We don't want any inequality constraints except the non-negative constraint. We just want equalities. All right, so how do we do that? Well, first of all, it's easy to change the maximize into a minimize. We just put a minus sign up front. Maximizing 2x1 plus 5x2 is equivalent to minimizing negative 2x1 minus 5x2. We'll just have to remember at the end to flip our signs around. Okay, so we want to minimize negative 2x1 minus 5x2, subject to some additional constraints. So the first constraint is that x1, let me maybe make a note as to how I'm doing this. So we changed maximize to minimize. I'm sorry for all the tapping, by the way. I know that it picks up a lot on the microphone. Okay, so x1 less than or equal to 4. How do we turn that into an equality constraint? Well, we add an extra variable x3, and we say that x1 plus x3 is going to equal 4. And we're going to also require that x3 is at least 0. So we can see that if x1 is at most 4, then we can find a positive x3, or non-negative x3, so that x1 plus x3 equals 4. And conversely, if x1 plus x3 equals 4, then x1 is at most 4. So if we add this extra slack variable x3, we end up with a problem that's equivalent to the inequality constraint. Or we end up with a constraint that's equivalent to the inequality constraint. So x2 at most 6, we do the same thing. We introduce a new slack variable x4. We can't use x3 again because x3 was tied to x1. So here we're going to get the equality constraint that x2 plus x4 equals 6. And we're also going to require that x4 is at least 0. All right, we also have x1 plus x2 is at most 8. We do the same thing. We add a new slack variable. This time let's call it x5. And again, we require that x5 is not negative. Okay, so if we just sort of recap what we did, our new problem is to minimize negative 2x1 minus 5x2, subject to x1 plus x3 equals 4, x2 plus x4 equals 6, and x1 plus x2 plus x5 equals 8, and x1, x2, x3, x4, and x5 are all non-negative. So this is the standard form of our linear program. So now once we have it in standard form, we can apply the simplex method to find the solution. So first of all, let's take the system of equations and translate it into a matrix. This is really just so we don't have to keep writing the x's all the time. So our first row, we have 1x1, 0 x2s, 1 x3, no x4s, no x5s. And we're going to make it an augmented matrix. So I'm going to put the right-hand side of the equalities on the right-hand side of the matrix. So we'll have 4, 6, and 8 on the right-hand side. Then our second equality, we had 0x1, 1x2, no x3s, 1x4, no x5s. And then we had 1x1, 1x2, no x3s, no x4s, and 1x5. All right, so this is the matrix that we want to use when we're applying the simplex method. And again, in order to jump right into the simplex method, we needed to be in standard form. All right, so the idea of the simplex method is we're going to start at some basic feasible solution. And we're going to move to other basic feasible solutions that reduce our cost function. So our cost function is the thing that we're trying to minimize, so negative 2x1 minus 5x2. So we're going to start at a basic feasible solution, and then we're going to move to adjacent basic feasible solutions, but we're only going to move to adjacent solutions that make the cost smaller. So the idea is as we go, we're going to get smaller and smaller costs, and finally at the very end, we're going to get to a point where we can't improve anymore, and that's going to be the optimum. Say adjacent basic feasible solutions. With lower cost. So in our case, a basic feasible solution, let me abbreviate it BFS, is a solution, or is a value, it's a vector, that satisfies the equality constraints and also the constraint of all of the variables being non-negative. So it needs to satisfy the constraints and have only 3 non-zero values. Right. So in our case, it's at most 3 non-zero values because our matrix has 3 rows. So if we had 3 equality constraints, a basic feasible solution can only have 3 non-zero values. If we had 10 equality constraints, a basic feasible solution could have 10 non-zero entries. Okay, so associated to each of these matrices, as long as it's in a good form, as this one is, we can just look, there's a standard basic feasible solution associated to it. So what I mean by having it in a good form is that we have a copy of the identity matrix. So the basic feasible solution associated to this matrix is, so we look at the columns that form the identity matrix. So in our case, that's going to be the last three columns. And we look at the first row of the identity matrix, and the associated entry there is 4. Right? Then for the second row of the identity matrix, we see a 6 in the column that we added, and for the third row, we see an 8. And then we put zeros in the other positions. So basically, we just wrote down the simplest basic feasible solution that we could find, right? If you multiply this matrix, so I'm ignoring the last column and just taking the matrix on the left-hand side. If I take that matrix and I multiply by my basic feasible solution that I just wrote down, well, you can check that first row dot product with this vector gives me 4, second row gives me 6, third row gives me 8. Right. So for each of the rows for each of the columns that wasn't part of this identity matrix, we put zeros, and in the other ones, we just put whatever we needed in order to make all the equality constraints hold, which was just the values of the last column. Okay, so again, this is feasible because it satisfies all the equality constraints, and it's a basic feasible solution because we have only 3 non-zero entries. Okay, so sometimes we say that this is like, that this identity matrix is like the basis corresponding to this matrix. So if we label the columns, let's say A1, A2, A3, A4, A5, our basis at the moment consists of A3, A4, and A5. So the idea of the simplex method is that we're going to say, let's choose one of the other columns, A1 and A2. Let's let that column enter the basis, and then someone else will leave the basis. Okay, so you can sort of copy the algorithm in the textbook in order to do this, but I think it's useful to sort of understand what's going on here. Otherwise, it's easy to get lost. So let me recopy this matrix just so we can easily follow along. So we had 1, 0, 1, we had 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, and 4, 6, 8. Right. So the things to think about is what happens if A1 enters the basis and what happens if A2 enters the basis. Right, so the basic feasible solution that we had associated with this matrix was 0, 0, 4, 6, 8. If A1 enters the basis, well, how are we going to have to update the basic feasible solution? Well, if A1 enters the basis, so keep in mind that the basis is the collection of columns corresponding to the entries in my basic feasible solution that are non-zero. So here I have A3, A4, and A5 corresponding to entries 3, 4, and 5 in my vector that are non-zero. So if I move to a different basic feasible solution where A1 is non-zero, that means I'm going to have to add some multiple of a vector that starts with 1. So this isn't notation that the textbook uses, but let me call this D1 for the first direction that I could move in. So I want A1 to enter the basis, so I'm going to want my first coordinate to be non-zero. That's why I put a 1 in the first coordinate. I don't want A2 to enter the basis, so it's going to stay 0. And now what do I have to put in positions 3, 4, and 5 in order to keep all of these equality constraints satisfied? Well, if I'm going to add something to my basic feasible solution already satisfies all the equality constraints. So I better add something that has inner product 0 with all of these rows. Right. So I put a 1 in the first coordinate. If I'm not going to change the value of the first equation, then I'm going to have to put a -1 in the third slot. Right? I have 1 times 1 plus 0 times 0 plus -1 times 1. That gives me 0. If I'm not going to change the second equation, well, then I better put a 0 in slot 4. And if I'm going to keep the third equation satisfied, then I better put a -1 in the last slot. Right. So the point is that if I add a multiple of D1 to my basic feasible solution, I get another solution that at least satisfies the equality constraints. Okay. So what happens to my cost function if I move in this direction? Well, everything's linear, so the way I compute what happens to my cost is I take the dot product with my cost vector. So the associated reduced cost is D1, or R1 is the notation the textbook uses. It's the dot product of D with the cost vector, where C is, well, if we scroll up here, we said that our cost was -2, -5, 0, 0, 0. Right. So my associated reduced cost here is 1, 0, -1, 0, -1, dot product with -2, -5, 0, 0, 0, which is -2. So this says, if I move in the direction which brings A1 into the basis, then my cost is going to go down at a rate of -2. Okay, so what happens if A2 enters the basis? Well, so my basic feasible solution is going to be updated by adding, let me call it D2 this time, for the direction if we want to bring A2 into the basis. So we're not going to change A1 because I don't want to bring A1 into the basis. I do want to bring A2 into the basis. And now I have to figure out what I have to do to the things that are already in the basis. So the inner product of each of the rows of A with my D2 needs to be 0. So that means A3 better be 0, or position 3, I better have 0. Position 4, I've got to have -1. And position 5, I also have -1. So that means if I take my basic feasible solution, I add a multiple of D2, all of the equality constraints are still going to be satisfied. So if I move in the direction D2, what's going to happen to my cost? So in this case, my reduced cost is going to be gotten by taking this vector and taking the inner product with the cost vector. If I do that inner product, I get -5. So if I move in the direction which brings A2 into the basis, my cost goes down at a rate -5. So my second reduced cost is negative. In fact, both of my reduced costs are negative. So I could choose to bring either A1 or A2 into the basis, and I'd still bring my cost down. Typically what we do is we pick the direction with the smallest reduced cost. So -5 is smaller than -2. We choose to bring A2 into the basis. So one way that we can think about what's going on is that we're taking the basic feasible solution that we already have, which was 0,0468. We're adding a multiple of D2, and that's going to give us another basic feasible solution. Now remember that we had the constraint that all of these variables had to be non-negative. So how much of D2 can I add? Well, I can only add D2 until one of the guys hits 0. Once one of the guys hits 0, then I can't move any further in that direction because then I'm going to start making some guys negative. So what are our negative entries of D2? Well, we have a -1 here and a -1 here. So the first -1, I see that I can only move 6 times D1 before I make something 0. And the second -1, I see that I can only move 8 times D2 until I make something 0. The smallest of those two guys is 6, so that means I'm only going to be able to move distance 6. So we expect that the next basic feasible solution will be our initial basic feasible solution, which was 0.00468, plus 6 times 0, 1, 0, negative 1, negative 1. Right, and again, I can't choose something more than 6, because if I chose something more than 6, then the fourth coordinate would be negative. Right, so all I'm really doing here is I'm looking at 6 divided by 1, I'm looking at 8 divided by 1, and I'm just seeing whichever of those is smaller. But if you think about it in this way, of just like adding an amount of a given direction, it's easier to not get confused, in my opinion. Okay, so we expect the next basic feasible solution is going to be this quantity here. This makes the fourth variable equal to 0. So we say that A4 leaves the basis. And we said that A2 was entering. So if we copy our matrix again, we had 1, 0, 1, 0, 0. Oops. 4, 6, 8. Okay. So A4 leaves the basis. Whoops, sorry, I copied this down wrong. I knew something didn't make sense. There we go. So A4 is going to leave the basis. So we look at the row where A4 has a 1. Right, remember we had an identity matrix in the basis rows. So there's only one row where it has a 1. So this is the row that we're going to pivot around. And then we look at the column for A2. So A2 was the guy that was going to enter the basis, so that's why we look at that column. And then we look at the row where A4 has a 1. So this is the entry that we're going to pivot around. All right, so now what we're going to do is just the elimination that we're familiar with from linear algebra. So I want to make the A2 column zero, 1, 0. Right, so I want the A2 column, so I look at the entry that I'm pivoting around, I want that entry to be 1, and I want the other entries to be 0. So I'm going to subtract the second row from the third row in order to make that happen. So if I subtract the second row from the third row, the first row and the second row are going to stay the same. And then I have 1 minus 0, that's 1, 1 minus 1, 0, 0 minus 0, 0, 0 minus 1, negative 1, 1 minus 0, 1, 8 minus 6, 2. So this is my new matrix after applying the first iteration of the simplex method. All right, so what's the basic feasible solution associated with this matrix? Well, so we're going to have zeros in all the columns that aren't part of the identity matrix. So the first column isn't, second column is, third column is, fourth column isn't, and third column or last column is. Right. So the 4 goes here. Right. This is the first column of the identity matrix in column 3. Second column of the identity matrix is in column 2, so that's a 6. And the last column of the identity matrix is column 5, so that one gets a 2. So my associated basic feasible solution is 0, 6, 4, 0, 2. Let's see if that agrees with what we thought before. We expected that our next basic feasible solution would be this quantity here. And in fact, we see that it is. We get 0, 6, 4, 0, because 6 and negative 6 cancel out. And then 8 plus negative 6, that's 2. So in fact, by doing this elimination, we got the basic feasible solution that we expected. Okay, so now we just iterate this procedure again. We think about the directions that we can move in, and we compute the associated reduced costs. You don't have to write out these directions if you don't want to. The textbook doesn't, but I find that it can often be helpful. And it's useful for understanding what's going on. So we can move in direction 1, so we could bring column A into the basis. And if we bring column 1 into the basis, we're only allowed to bring one new guy into the basis at a time, so we won't bring column 4 into the basis. All right, so if I'm gonna make all of these equality constraints continue to hold, I need this vector to have inner product 0 with all of the rows. So that means I need a negative 1 in the third position. I need so if I look at the second row, I'm gonna need a 0 in this position, and in the final position, I'm gonna need a negative 1. So notice what actually happened here. So the first entry, that was the entry of the guy that we wanted to bring into the basis. That guy I just chose to be a 1. And then the other guy that I wasn't bringing into the basis in row 4, that was a 0. So these were the guys that were not in the basis. And then we end up with negative 1, and 0. So really where those numbers came from is they're just the negatives down the first column. So if I read down the first column, I get negative 1, 0, negative 1. And that's what you end up seeing here. I have a negative 1 in the column or in the position corresponding to the first column of the identity matrix. I have a 0 in the position corresponding to the second column of the identity matrix. And I have a negative 1 in the position corresponding to the third column of the identity matrix. So really all you have to do is read down the first column put negative signs there, and then be sure that everything's lined up based on how the identity matrix is arranged in your matrix. It's easy to get confused. That's why I like to write down this vector first. So the associated reduced cost to this direction is I'm just going to take the inner product with the cost vector. Right, the cost vector was -2, -5, and then zeros. So this reduced cost is going to be -2. So if I bring the first column into the basis, my cost goes down at a rate -2. Okay, who else could I bring into the basis? Well, the only other guy who's not in the basis is column 4. So what direction am I going to move in if I bring column 4 into the basis? So we can work it out the same way. If I bring column 4 into the basis, I'm going to move in the direction 0, -1, 0, 1, 1. And the associated reduced costs is going to be, well, again, cost vector was -2, -5, and then zeros. So my reduced cost in this direction is going to be +5. So that means if I travel in the direction of bringing column 4 into the basis, my cost is actually going to go up at a rate 5. And that makes sense because I brought, right, if we think about what we did on the last iteration, we said A4 left the basis and A2 entered. So if we decided to bring A4 back into the basis, we'd sort of just be undoing what we already did. Right, so we expect that we're not going to bring row 4 or column 4 back into the basis. And we can see that because the reduced cost is positive. So there's only one reduced cost that's negative, R1, so that tells us we're going to bring column 1 into the basis. All right, so our basic feasible solution was 06402. If we move in this direction D1, who's the first guy that's going to be zeroed out? Well, it's going to be the 2 entry, because 2 divided by 1 is smaller than 4 divided by 1. Right, so what that tells us is that A1 is going to enter the basis, and then A5 is going to leave the basis. Right, so now we do our pivot step. So we're bringing A1 into the basis. That means we look at the first column. Said A5 was going to leave the basis. So the entry in column 5 with a 1 is in the last row. So that means this is our pivot column. So now I need to zero out all of the other entries of that column. So if I do my pivot step, I'm going to subtract the last row from the first row. So second 2 rows are going to stay the same. So 1 minus 1 is 0, 0 minus 0, 0, 1 minus 0, 1, 0 minus -1, 1, 0 minus 1, -1, 4 minus 2, 2. and I end up with this new matrix. I should mention that if the pivot was not 1, so if the pivot was like 2, then we'd have an additional step in our pivot step where we'd divide the last row by 2. It's exactly like doing elimination with matrices. Right, so you'd make your pivot 1 first by dividing by whatever you need to, and then you would subtract. You'd subtract multiples of that row from the other rows to zero out all the entries. It's exactly the same step as Gaussian elimination. Okay, so we do our pivot step, we get this new matrix. The associated basic feasible solution is, well, we have zeros in the rows that don't correspond to the identity matrix. And then we're going to have 2, 6, and 2 as our other entries. So this is our associated basic feasible solution. Again, notice that it's just the last column, possibly reordered, but in this case it's not, just because the last column happens to be a palindrome. So it's really like the last 2 corresponds to the first 2. Okay, so anyway, that's our basic feasible solution. Now we want to think about the reduced costs. So we can go through exactly the same kind of procedure as before. So there's 2 options for what we bring into the basis. We can bring column 4 into the basis, or we can bring column 5 into the basis. So if we bring column 4 into the basis, if we go through the same type of calculation as before, we get that the reduced cost is 3. If we bring column 5 into the basis, we get that the reduced cost is 2. So how did I calculate this? Well, the direction that I could move in, if I wanted to bring row 4 into the basis, was 1, -1, -1, 1, 0. And I dot product that with the cost vector. If I want to bring row 5 into the basis, this is the direction that I end up moving in. And you dot product that with the cost vector. So here I notice that both reduced costs are positive. So we're done. So we found the basic feasible solution that optimizes our standard linear program. Now we know by the fundamental theorem of linear programming that this is actually the optimal solution for the entire linear program. Right? Even if we allow ourselves solutions that aren't basic feasible solutions, there will be a basic feasible solution that's optimal. All right, so we found our optimal basic feasible solution. That's the solution to our standard linear program up here. And then if we think back, what did we want to do? We wanted to find x1 and x2 that we wanted to find x1 and x2 that maximize 2x1 plus 5x2. Well, those are going to be the same values that minimize -2x1 minus 5x2. So the optimal solution for our original linear program so we'd have x1 is 2 and x2 is 6. And that's our final answer. All right, so in the next installment, I'll talk about the two-phase simplex method and also how to make this a little bit more streamlined by drawing a tableau.